Hi, my name is Ming, and I'm the co-author of this paper. Unfortunately, I could not be here in person today, but nevertheless, here is the presentation on the application of VR in fall detection. Currently, in the area of healthcare, it has been shown that falls are a major cause of injury in senior citizens, and a significant impediment to independent living. Studies have shown that early detection is one of the key factors toward reducing the severity of fall-related injuries. Thus, it is important in the domain of public healthcare to develop an intelligent fall detection system that can track and notify responsible personnel in a timely manner. In recent years, the development of fall detection has shifted toward the usage of AI and computer vision. However, the lack of training datasets serves as a major obstacle toward progress. This research aims to fill that gap using virtual reality simulation capability to develop the necessary training datasets. For the purpose of algorithm training, there are a few publicly available fall datasets: UR fall, multiple camera fall, and fall detection. These datasets, however, suffer from similar problems: lack of diversity in fall scenarios and data recorded from actors with different physical condition to the targets. In addition, these limitations are hard to overcome due to a variety of issues, in particular privacy concerns when it comes to recording real-world data. This is where VR can thrive. In other areas, VR has been used for dataset generation for the training of algorithms. In particular, the parallel eye vision framework, which has been used for traffic vision research, showed a marked improvement in algorithm accuracy when the virtual dataset was used for pre-training the model, and then fine-tuned using real data. For this particular research, the methodology involves the following steps. First, the humanoid model is generated using MakeHuman, an open-source 3D graphics software designed for prototyping photorealistic humans. The model's characteristic can be tweaked, allowing for a variety of simulation scenarios. Next, the full simulation is generated using Blender to animate the model. The animation will be generated by inverse kinematics and supported by motion capture data as well as physics-based motion generation using machine learning. And finally, the four scenarios are formulated and then generated in Unity. Based on this, the following case study was conducted. 3 datasets are examined, 1 virtual, 2 real. The virtual dataset was rendered in Blender using the MakeHuman model, and the 2 real dataset are motion captured using a HTC Vive. The full simulation will be conducted with Unity under the default lighting with 5 cameras, 2 front, 2 back, and 1 top. The fall detection algorithm used is proposed by Noise Macros, etc., based on VGG16 convolution neural network. The flow scenario are converted to optical flow images using TVL1 optical flow algorithm as required by the detection algorithm. The results are as follows. The initial testing showed poor performance with sub 80% accuracy for all 3 datasets, with the virtual dataset performing the worst at 61.3%. This level of performance is quite poor compared to the claims of the author. Next, the back and top camera were disabled using only the 2 front camera for the dataset. This shows a marked improvement over the previous result, with accuracy over 80% for all 3 datasets and over 90% for the real data. This indicates that the algorithm has failed to detect falls from footage from the back and top camera. From there, these observations are made. First, the algorithm lacked variety in the training data in regards to the angle of image capture. It's likely that the performance could be improved using a wider variety of training data. And second, the virtual fall reality footage are sufficient to trigger the fall detection algorithm, even if the performance is slightly inferior to that of the real dataset. This indicates that this approach can generate usable data for the training of AI, either independently or in conjunction with real data for fine-tuning. In future works, this research can be expanded in differing directions. The 4 dataset variety could be improved using 2 different motion tracking systems, the HTC Vive and the OptiTrack, to provide data instead of just the HTC Vive. Algorithm training will also be done using a combination of VR-generated and motion captured data, and its performance compared to algorithm trained purely with real data. Additional sensors such as accelerometers and deep camera will also be added to provide additional dimensions to the dataset. And lastly, the proposed approach will be tested in other fields to compare results. Thank you.